So let me continue with my third example. We have been considering the quotient of the polynomial ring over K by the ideal generated by an irreducible polynomial P. And we have seen that this is a field. I would like to say the same thing in a slightly more sophisticated language, but it amounts to the same. Instead of writing down the Bézout equality, one can also say that an ideal generated by an irreducible element of K of x is a maximal ideal, and the quotient by a maximal ideal is always a field. So alternatively, one can say that P is a maximal ideal of K of x, and the quotient over ring by a maximal ideal is a field. But of course, the proof of this amounts to the same Bézout equality. How do you prove that P is a maximal ideal? You just consider some potentially bigger ideal, that is to say, containing P and some element Q not belonging to the ideal generated by P. This Q is going to be prime with P, so you can write the Bézout equality, and it is in this way that you see that such an ideal will be necessarily equal to the polynomial ring K of x. Okay, so this is an extension of K in an obvious way. Maybe here it's even better to say that it's an extension of K because it's a K algebra. Is a K algebra. Hence, an extension of K and let me give you a more concrete example. Let's take K equal to the field of two elements. So Z by 2Z. It consists of 0 and 1, and 1 plus 1 is 0. Let us take P equal to x squared plus x plus 1. So this is an irreducible polynomial over F2. Then K of x modulo P is a field of 4 elements. It contains 0, 1, the class of x modulo P, let me denote it by x bar, and the class of x plus 1 modulo P, let me denote it by x plus 1 bar. And you see that x bar squared is equal to minus x minus 1, since you know that x squared plus x plus 1 is 0 in our field. Well, the characteristics is 2, so minus 1 is the same thing as 1, so it's just x plus 1 bar. In the same way, x plus 1 squared is x bar, and they are inverse of each other. X squared times x bar times x plus 1 bar is 1. So this is the structure of a field of 4 elements. The cardinality of K is 4, One writes then K equal to F4. Well, this might be strange at the first sight, because we only know that K has 4 elements. And if you write F4, it you somehow mean that there is only one field of 4 elements. Well, it is true. There is only one field of 4 elements. In fact, all finite fields of the same cardinality are isomorphic, and we will see it very shortly. Okay, now let me talk about algebraic elements. So I have a field extension, K in L, and I take alpha in L. I say that alpha is algebraic if I can find some polynomial, if there exists a P in K of X such that P of alpha is 0. Otherwise, I say that alpha is transcendental. Alpha is transcendental. So this is a definition, of course. Well, let me give you a lemma. So if alpha is algebraic, then there exists a unique, unitary polynomial of minimal degree with this property. Such a polynomial is irreducible. Any other polynomial with this property is divisible by P. Any Q, so let me call this unitary polynomial P, any Q such that Q of alpha is 0 is divisible by P. One calls P the minimal polynomial of alpha over K. Such P is called the minimal polynomial of alpha over K. So the proof of the lemma is very simple, of course. It is a direct consequence of definitions. Well, let me say it in sophisticated terms. We know that K of X, the polynomial ring in one variable, is a principal ideal domain. And the polynomials vanishing in alpha certainly form an ideal. So, this ideal is generated by one element. Let me denote this set by I. So I has a generator P. And this is certainly a unique up to a constant element of minimal degree in I. P is unique up to a constant element of minimal degree in I. Furthermore, if P was not irreducible, if P is Q times R, then P of alpha is Q of alpha times R of alpha. So Q of alpha or R of alpha must be 0, which is a contradiction with the minimality of the degree. Then Q of alpha is 0 or R of alpha is 0, and this contradicts the minimality of the degree. If you are not familiar with the fact that the polynomial ring in one variable over a field is a principal ideal domain, you are strongly encouraged to learn this. This is a very simple fact. It is a consequence of Euclidean division, and this time I will not give any more details on this.